Tsvi. Tsvi, the General Manager of the NEC Corporation Research Center in Israel, which is, I think, the only innovation center outside, right?
Outside Japan?
Outside Japan.
I'll give the details in a second.
Okay. So, thank you, Tsvi.
Okay, can we put it up?
Yeah.
Okay, great. Okay, hi everyone, I'm Tsvi. And when I talked to Professor Shapira about coming here, she told me, look, I know you city slickers from Tel Aviv, from the multinational corporations. You always come and do PR and trying to recruit people. So we are trying to recruit people, but I'm going to try to give a real scientific talk with content. My promise to you is within these 20 minutes, I will offer you a mathematically rigorous, well-defined definition for explainability and show you a case where we were able to apply it. And if I'm right, it should be interesting. So about explainability. So still, 3 slides about NEC. So that's a picture from the lab of Thomas Alva Edison. And the guy on the left, you can see the short guy, is Japanese. He worked for Thomas Edison, and then he went back to Japan and established NEC. And at that time, NEC was into electricity, light bulbs, and early telephones. That was 120 years ago, so I cannot say we're a young, spicy startup. But we do some pretty cool stuff. For example, the inventor of carbon nanotubes, still waiting for his Nobel, like the late Amos Oz. I hope he makes it, because Japanese people live a long time. That was 25 years ago. That was NEC. Quantum annealing, not quantum computing, quantum annealing was actually NEC, also waiting. Actually, chances are heating up in the last few years. This picture here, you can find it on YouTube, the people looking with the face detection. Okay, we've seen so much face detection. This is from 93 or 94. The video is on YouTube. And there was a young guy in Princeton working at NEC called Jan LeCun. Maybe you've heard his name. And he had the crazy idea to apply convolutional neural networks to do face detection. Silly idea. We also make spacecraft that use AI. The Falcon 2, it's called Hayabusa in Japanese, is the first spacecraft to reach an asteroid, land on it, take samples from it, bombard it, shoot it, take some more samples. It's in orbit currently, and hopefully within a year it will be the first to return actual samples from within an asteroid. And it uses some AI because it's 1 light hour from the planet, so we cannot really tell it what to do all the time. We also do high-performance supercomputers, not GPUs, but like Vector, what's known as HPC, the kind of thing that people use for weather prediction, etc. We're 100,000 people, $30 billion, and in Israel we're just 30. I hope that number increases. Okay, end of PR. Okay, so our journey, which led us to this definition of explainability, started with something more mundane, precision and figuring out the relationship between precision and other important things in AI. So the recent surge in AI, the reason everyone is here at this late hour after lunch, instead of being somewhere else, is the recent success of AI, deep neural networks, etc. What was the real success? The real success was in 2 things. First, in digital marketing and advertising, also known as recommendation engine. A recommendation engine which recommends ads is called an ad engine. You know the company. It's very easy to know if there's a big company which does that. It's very easy. They never mention the word advertising. They mention saving the people in Africa. They have a colorful logo and everything, but it's an advertising agency. And it makes a lot of money for these big internet giants, right? Because it's better than the other methods. It produces more clicks, more sales. That's the criteria. On the other hand, in deep learning based for images, ImageNet succeeded supposedly better than everything before. So people academically became interested. But we know already, I'm going to speed up because otherwise I'm not going to get to what I promised you. We know that now we have to start explaining a lot of other stuff. At first, people became concerned that maybe when you recommend things to consumers, there's some inherent bias, that if you're a single mother of color in a bad neighborhood, you will never get the good advertisements for good jobs or good housing. You will get advertisements for cosmetic surgery, laser treatments, etc. So at first, of course, people said, it's AI, it's deep, it cannot be changed. All the big companies said, there's nothing you can do. And then the regulator said, well, I don't like this tone of voice. So now they're actually changing. They realize it's important. So that's in this area. Another area, you saw a presentation about cars and autonomous cars. It is not enough that the autonomous car will be better on average than a driver. Not just because people are stodgy or regulators like to interfere, but one of the problems you should all be aware of, maybe you already are, is stability of the ROC curve, okay? It's not enough to get the best on your data set and then launch it. What if it changes? What if you trained your car for all the foreseeable conditions and then it's Seattle in the winter and Mount St. Helens erupts and you have a lot of those dust particles which you never had in the training set? What happens then? So if you don't understand the failure mechanisms, it's very hard to predict how this will behave. Third example, medical diagnostics, where I'm also going to give the applied example of myself. Some very smart, way smarter than me, people said recently that soon radiologists will not have a job. These radiologists will have a job even if the smart people will not have, okay? Nothing is changing. Why? Because you need someone you can blame if there is a misdiagnosis, okay? That's the way the real world works, okay? Nobody cares if the Google system can predict cancer better than anything else based on their data set, because you have to come to a 65-year-old person whose health is not great and say, we want to do a biopsy, which, by the way, has a risk because we think you might have cancer, okay? And you do that all the time, but you cannot do that based on an algorithm. What happens if it is one of the 2% cases where there's actually a complication and he ends up being disabled or dead because of that? Are you going to blame the algorithm? Are you going to give him more advertisements? Not going to fly. So that's why you need also stability and compliance. So let's get a little more specific and then we'll get to the explainability measure we offer. So one concern is ROC deterioration, meaning it worked well in the lab or in your hospital or in your plant, you sell it to other people, it doesn't work as well. Frankly, I'm not aware of a single case where ROC improved with time or with change of place. It always deteriorates, but it can deteriorate a lot or it can deteriorate a little. You must quantify that. Another issue, different errors have different pain with them, okay? And explainability must be in the customer terms. Telling the customer, well, the explanation is that these 10,000 vectors were multiplied with this and gave this, that's not really an explanation. Okay, so some concrete examples. You can read the upper ones, I don't have time to get into that, but I think it's quite self-explanatory. The NLP one is important. That's a real thing which was published about 2 months ago, okay? When you look at the medical records of a cancer patient, in order to figure out if they had a certain test done to them or not, you need to read unstructured text written by medical people. If you're a doctor, you can read it and you will know with 100% assurance whether the test was done or not. You can train a nurse to do that, but it's expensive in terms of time. So they trained an NLP system to figure out, so again, it's not diagnostics. It just had to read the report and say whether patient A had treatment B applied to her or not. That's all, just to understand the medical text. And they did it, and it worked great, and it was in Seattle. And then they sent it to a very different place, Kansas, okay, to a big hospital, and it didn't work. Can you guess why? All the training was fine, they did train tests and everything. Can you guess? Exactly, because at the end of the day, it's only about 3 or 4 oncologists who fill those reports, and the ones working in Seattle are not the same ones as in Kansas, so their phrasing was different, okay? And we're all very glad they checked, right? Because it would have been really bad if they didn't. Okay, so I said we should delve deep, so I'm going deep. We are talking now about medical, okay, explainability, meaning if we reach some conclusion, how can we explain it? I don't think I have time to talk about that. I just mentioned finding similar labeled cases is a novel way. The other are not so novel. You might know them already. But finding similar previously labeled cases is a very good explanation usually. Why? In law, in medicine, that's the rule, right? You find a previous case, which looks very much like the current, and you say, 3 physicians said this is X, or even the outcome was X, everyone feels more secure. That's a good way to make an explanation. But how do you do that? So we all know to reach high precision, you need to understand the problem better. On the right-hand side, you can see a system, that's a Hinton paper as part of the Google Brain team, where they actually were able to classify MNIST with 4 stages of comparing with filters, just that, very simple computation. So it's easy to understand, but it only gets 95%. Turns out, getting from 80 to 90% in most problems is not interesting. I know there's a lot of papers like that. No one, frankly, reads them. No one cares. Getting from 95 to 99, or even from 98 to 99, that's interesting. And then the calculation becomes more complex. So, practical example that you all will understand, okay? Let's play a game. Let's assume you have a customer, an MNIST customer, and you provided a system to do MNIST. And we all know you can get 99% nowadays, or 98%, that's very easy, and you show the customer. That was what we initially were trying to solve, just improving the system. And there's this mistake up there. Some people write the 7 like that, and the MNIST, your code fails on that, okay? And the customer is not happy. He says, no, some people may write like that. I don't care if it's 1.1% or you have only 3 or 4 samples. I want you to solve it. I want you to fix the system. I don't care about your SOTA, and I don't care about the papers. I don't want any more mistakes like that. So what do? That's still not explainability. Well, basically, you do advanced augmentation. Basic things like affine and others that were mentioned are not enough. You have to do things like bicubic splines, deformations, topology-preserving deformations, and you get better performance. But then we started thinking, okay, so we were able to train the system based on taking a bad example and augmenting it in a clever way with some transformations, which are not the standard ones. Does it really even have to be a natural example? Maybe we can just draw an example of what we understood the system fails at and teach based on that. And we found out we could. Okay, it worked. So then we started thinking, okay, what is really the definition of what we're doing here? And can we use it for something else? And this, frankly, is the only important slide in this presentation. And if you feel it's wrong, or if you feel you don't understand it and want to understand it, please contact me. That's a mathematically rigorous definition of explanation. What does it mean? You can see the pictures. The pictures are the explanation. Basically, if, let's say it's the game, you're the providers or the customer, and the customer says, this one you labeled wrong. Okay, I think it's a mistake. If you can show him that, or her, that there's a previous example in the training set, which looks quite like it, and you can reach it in a continuous transformation, and it's the same label all the way, you have solved it. The explanation here is basically either the customer is wrong, or you're wrong, or the transformation reached an area which is not legal. So look at these 3 examples. Let's say the start frame is an example where the customer is not happy with the result, or you're not sure you're happy. The end state is an example from the training set. And there's a continuous transformation where all throughout the transformation, it stays the same label. That's an explanation. Think it over. It's both useful and it's conclusive. There's no way around it. Okay? Now, you might look at the picture below. That's why it's not trivial. Okay? So for example, let's say we classified this as 1. And the customer says, that's not a 1. That's a 7. Or say, no, look. We have this transformation. We start from this sample, and we continuously deform it, and we reach the 7. So it's a 1. What will the customer say? Or what will we say once we realize what's happened? We reached an uncanny, undefined area. The transformation was continuous, but the class did not stay the same. This is something which cannot or should not be classified. It's very important. What I tell you now is irrelevant for ImageNet and for almost any problem. If you don't acknowledge there are cases where your network should not give a result, you have a serious problem. Okay? Everyone knows here the example that the nice example of a rabbit that turns into a duck. It's continuously, right? It's continuous. But in the middle, there's a region where actually you didn't define how you want it to be treated. Okay? So that's explainability. Now, I have about 3 minutes, so I'll try to show quickly. So I claim this is a rigorous definition. You can program something to test if the definition has been implemented. There is only one problem. You still have to find this transformation, right? It's one thing to define a path integral. It's another thing in physics to calculate it. So can you actually, okay, so for this problem, when we were doing the precision, we found the transformation. I don't have time to give you the details now, but if you come, I can give you the reference papers. We built this transformation for MNIST. But MNIST is not a real problem, right? It's been solved by many other ways. It's a nice exercise, but that's it. Can we apply to other problems? Yes. but it's not immediate. You have to figure out a lot of stuff along the way, which is new for every problem. There is no some machine, you just push it in. So I'll just show you the example, and then maybe you'll want to ask me about it. So this is the medical example. It's a real medical thing. Diabetics develop sometimes something called retinopathy, which can make them blind. Okay? It's a global phenomenon. Hundreds of millions of people may have it. So first phase is you take a picture. It's very cheap and easy. And then ophthalmologists try to label it. They just make a decision, but they can also tell you where are the blood vessels. It's not a very hard problem to explain. Okay? Meaning, I take any one of you who has some measure of ability to work a little harder and look at pictures. Within 2 examples, you will know what is a blood vessel and what is not, and you'll be able to label as well as ophthalmologists. So it should be easy to classify, to make DNNs do it. And indeed, people have been doing it. So you can see on the left RGB bands of 3 different DNNs. Where they're white, it means they all agree. Colored meaning they disagree. Okay? They look really good. They're actually very good in terms of performance of percents, but they still make silly mistakes a person never would. You can see to 1, they just thought they saw something where there is nothing there. Okay, that's and the bottom one, you see a disconnected blood vessel. Now, there's something everyone who works in the area and everyone who's shown a picture will understand. Blood vessels are continuous because something flows through them. But apparently, we were not able, despite having thousands of examples, the network didn't learn this simple rule. It does very well statistically, but these kinds of mistakes are destructive. So we must find some explainability criterion which will help us improve it in these cases. To explain why it made a mistake. Just to explain it's not so simple not to make the mistake, look at this. Okay, I'm running out of time, but basically this is the grayscale information properly scaled. You see that when you look at it the way the network sees it, it's not so easy. So people are better because people can connect lines in their heads and apply some higher logic. But how do we teach the network? How do we find an explanation for the network when it fails so we can generate more examples? So basically, that would be an explanation in this case, right? I mean, like, we find a case where the network was mistaken. On the right-hand side, we took a patch where there's no blood vessel. On the left-hand side, we took one where there is one. We do a series, I show you discrete steps, but it's a continuous transformation, okay? And we reach a stage where they're actually visually pretty much the same, which means we have an explanation. I'll just show the final 2 slides, and then I'm done. Okay, I'm not going to be able to detail. There's a lot of math here, okay? Not applied math, but a lot of it. We had to combine 3 or 4 different technologies. It took some time. I'm sure others would have done it better, but that's what we could do, okay? Basically, I want you to see this slide just to explain. So basically, what you see here is a test example where each point which we could explain, meaning we found a sufficiently similar training patch which we could transform to it, is white. So points in purple are the points where we didn't have a full explanation. Doesn't mean there's no explanation, meaning that there is a mistake, that we are not covered yet. We don't have enough. Our algorithm for the transformation is not perfect. But you can see it's quite good. And this is perhaps the last one, because it shows something which is not trivial at all, actually. On the left-hand side is a sanity check, meaning we took a network, we took a blood vessel image, which was in the training set, and we said, can you fully explain it? Yeah, it could. Okay? That's the left-hand side. So just sanity check. But look at the right-hand side. We took an image, a legitimate image, and we illegitimately added to it something which doesn't happen in nature. We added digits. Okay? And indeed, you see them all in purple? The network could not explain that, meaning it said, I did not find any previous trained example that I could get from here to there. So I don't know what that is. Okay? I'm over time. You may have questions. So thank you very much.
Thank you very much, Tsvi. We have time for one quick question. If anyone has like one quick question. Here. Okay.
Done?
So you showed how you can explain some things, but what if how can it be used to explain anomalies? So things you can explain because you haven't seen them before in the data, or you've seen them very underrepresented in the data.
Very good question. Our definition of explainability is not the only one you could use, but it's very rigorous. It's an explanation for a case where you disagree with the network result. Okay, meaning we can't provide you necessarily an intuition into why the network says something, but we say, let's talk about the classification problem. Network said A, you claim it is B. Okay? We can do one of the following thing. We can find past examples which were labeled and a continuous transformation, and then we can look at the network all along this transformation. If it stays the same, and the transformation is legal, it means the network is right and you are wrong. If it switches in the middle, it means the network is wrong, and that's exactly the area where you should train it. And that's, by the way, that's very important. Everyone who's actually been in the real world knows you have some performance, then you need to get better for performance. So you have some annoying examples where you fail. What do? You say, okay, let's increase the weight of this example. Let's force the network to acknowledge it's wrong there. That works only to a certain level. Other people will say, okay, let's use standard augmentations. Shift, rotate where it applies, and that helps somewhat, but not always. We went further before we discovered this and said, okay, let's do deformable transformation. That was even better. Okay, but then we realized actually that is real explainability that you can use to train. Basically, explainability and the connection between it and improving a network is if there is a continuous path, like I mentioned, and the network started saying A and then ended up saying B, the network has a problem. Either the area in the middle is what's called uncanny valley. You don't want the network to predict anything there. That's a whole different topic. We did a paper on that last year. Or you want to retrain the network, especially in that region. And of course, this only works on continuous things. I don't know how to apply this to NLP or to discrete. I have no idea.
Thank you, Tsvi.
Thank you.
I know people have more questions, but...
I'm still here.
Yeah, you're still here.
Right. Thank you.